field, but not to electrons, but to either protons or more heavier atoms.
Yeah, so I'm doing infrared absorption by just observing the harmonic oscillator. So infrared spectroscopy, basically just you're shooting an electric field at like the bonds, and then you're observing how that bond reacts. So there might not be like a high absorption, and then at other points there'll be a strong absorption, and then depending on the absorption peaks, it relates to various bonds. So it's basically a little introduction. So using infrared spectroscopy, you can identify various functional groups just by observing their absorption peaks. IR uses external oscillating electric field described in the system right here, and to basically absorb these peaks. The electric field interacts with the charges of the dipoles, causing it to oscillate back and forth. And then, so basically this equation right here describes your total Hamiltonian by your initial Hamiltonian, and then, actually the dipole, or this is your initial Hamiltonian, and then this is your dipole of the electric field, and then that changes. And then if the molecule is nonpolar, this over here should be 0. Just because there's no, it just doesn't oscillate, or there's no effect due to the charges of the molecule. And then, so basically this is describing the overall idea is by applying energy to this bond, it'll oscillate at different energies depending on the bonds. Frequencies, yes. So here I just have 2 video representations just describing, you'll see there's a yellow line and a red line, and then they just describe your electric and potential energies, and you can see how they're different. And this is just a value I chose, and then you'll notice this is the peak where it was observed later. I'll show you your graph, and you can see how the energy of this system is a lot higher than this system.
And the energy, you mean frequency?
Yeah, frequency.
Just in atomic units, the equivalent.
Yeah.
It's frequency, how frequent electric field oscillates.
Yes.
Okay.
Yes. So that's for you. So then you can just notice they kind of stay kind of just near each other. There's not a lot of movement compared to when the absorption peak was observed. You notice that there's a lot more energy of the system.
So it accumulates energy much quicker.
Yes.
At a certain. Okay. We can launch both at the same time. That's cool.
Okay, so here I changed from that initial equation, I changed the omega, or the W value of the energy system that was being applied. And then you can see that this is just, I varied that W value over time, and you can see that how the energy accumulates over time. And so these are just a bunch of various energy levels or frequencies. And then this 0.1 here is where you'll absorb the frequency peak, and you see that it's substantially higher than the other values.
And what is on the Y? Energy? Total energy?
Yeah, total energy.
Versus time. Okay.
Yep.
So your energy is not conserved. It's growing.
Yes. So here is my absorption peak. This was observed at 0.1, so this is where you can see that the total energy is like the highest. So that's when the bond between when you use your infrared and you'll observe that the bond right here is at its highest. So this is useful just for observing different peaks in molecules. And then, but you can see that at other values, there's not a lot of energy until you hit this 0.1, and then it just decreases significantly. Overtone is just defined as a factor of the natural frequency. So the natural frequency in the system was determined to be a 0.1, and then in theory there should be in each factor of the frequency there should be what's called an overtone. And then so here is where I've observed my initial frequency, and then in theory there should be another overtone at this 0.2 value, but this was not observed. So then this is at 0.2, this wasn't observed, and then in reality, or in theory, there should be another overtone at 0.3, and so on. You have any questions?
Okay, let's thank Dylan. I know who will ask questions. Okay.
So, are you only simulating a diatomic atom?
Yes.
Okay, because I don't think the approximation that says if it's a nonpolar atom, the D will always be 0,
Yeah.
which then means that you should never see IR peaks
Yeah.
in a nonpolar.
Yeah. Yeah. So we were just observing diatomic. I just didn't read that very clear.
Okay.
More questions? If no, let's thank Dylan once again and move on with the program.